So limits have a lot of very convenient properties that make calculating them a lot easier than trying to use the definition. Now, the first property is the first actual limit that we're seeing how to calculate. So to see what's going on here, think about what the graph looks like. Our function here is a constant. F of x equals k. For example, f of x equals 3 or f of x equals -2. The graph of that function is going to be a horizontal line. Now, regardless of what value we pick for a, the point here is going to be a comma k. So the function is going to be doing the same thing here on each side. From the right, it's approaching k, and from the left, it's also approaching k. So that's going to be the limit. So for example, if I ask for the limit of 6 as x approaches 2, that's going to be 6. In fact, the number that I put down here doesn't matter. Regardless of the number you use for the x value, you're going to get the same thing for the limit. Okay, well, the next step up from a constant function is a simple linear function, like f of x equals x. And again, it's going to be helpful to look at the graph. Now, if we pick any value for a, then this point is going to be a comma a. So as x approaches that value from the left, the function approaches a, and from the right, it also approaches a. So that has to be the value for the overall limit. So for example, if I asked you to find the limit of x as x approaches 2, the answer would be just 2. All right, so these two new properties here give us tools for splitting up big limits into smaller ones. The first one says that the limit of a sum is equal to the sum of the individual limits. And the second one says that the limit of a product of two functions is equal to the product of the individual limits. So with these two tools, we can start doing bigger limits without always having to go through the business of drawing graphs or going through the definition. So take a look at this limit. We can split it up first using the third property to and then we can split the first part up using the fourth property to this. Now, we've drilled down to individual limits where we know what each one is based on the first two properties. Property 1 tells us that this first limit is 3, and the second limit is 2. And property 2 tells us that the middle limit is 2. So now we can get the final answer with just a little arithmetic. Property 5, the new one here, does for exponents what properties 3 and 4 did for sums and products. The limit of a function to a power is equal to the limit of the function raised to the power. With one warning, both limits have to exist. You can run into a little trouble, for example, when the exponent is a fraction. That is when you're working with things like square roots, and we'll see some examples of this in a later lecture. So now that we have these properties, we're in a position to work with a much larger group of functions. For example, look at this polynomial. First, we can split it up into 3 parts using property 3. Then we can split the first part up again using property 4. And finally, now we're going to use property 5 to move the exponent outside of the limit. Now I've done the same thing as I did in the previous example. I've broken the original limit down to a bunch of smaller ones, whose values I know from properties 1 and 2. The limits of the 2 constant terms are 2 and 1. The limits of the linear terms here are both 2. So now I can get the final answer by just simplifying the arithmetic. Now, that was a lot of work for just one limit. But we can generalize what we did here to get a method for finding the limit of any polynomial, and that's property 6. It says, in other words, if we want to find the limit of a polynomial, all we have to do is evaluate the polynomial at that value. So to find the limit to the right here, all we have to do is evaluate the polynomial at x equals 1. So 6 is the final result. All right, so before we move on to looking at specific examples of limits, we need one more property here. Property 7. This is the division version of property 4. It says the limit of the quotient of 2 functions is equal to the quotient of the 2 limits. And again, we have the same little warning here as we did with property 5. This assumes that the limit in the denominator is not equal to 0. Okay, well, since property 6 gives us a way to find the limit of any polynomial, if we combine that with property 7, we can find the limit of any rational functions. For this example, property 7 lets us split the limit up into a top part and bottom part. But those limits are each just a polynomial. So property 6 tells us that the upper limit is 3 times 1 to the 4th power minus 2 times 1 squared plus 5. And the bottom limit is 2 times 1 minus 3. So simplifying this, what gives us 6 over negative 1, which is just negative 6. Okay, now keep these ideas in the back of your mind, right? Or make a list on a notepad that you can refer back to. In the next 2 lectures, we're going to look at the limits of specific functions, and we'll be referring back to these properties along the way.